is just like the question we did yesterday in class with Tyler going to the bumper cars. But this time, and let me flip over to where he's at. But this time, Diego, Lynn, and May are all going to the bumper cars at the same time that Tyler went to the bumper cars, okay? So if you guys don't remember, we're going to start with Tyler just to jog your memory on how he went to the bumper cars. And if you remember that he was able to get to the bumper cars, which was 50 meters away, and it took him 40 seconds, okay? So I'm going to do this right here, 50 and 40, and I'm going to put, for Tyler, I'm going to use just a single dot, and this is going to be Tyler's journey to the bumper cars, okay? So you need a single dot right there at 40 and 50, okay? And we can even label it Tyler, okay? So that's Tyler's journey to the bumper car, all right? And remember, and we can even take a straight edge and just use the edge of your book, draw a straight line between Tyler and 0, 0. Now, Diego, on the other hand, he left the ticket booth at the same time as Tyler. Okay, so when his starting point is going to be down here at the same time as Tyler. All right, now he jogged ahead at a steady pace. So if it tells us that Diego is going at a steady pace, then that tells us that this is a proportional relationship and that it should be a straight line. Okay, and he reached the bumper cars in 30 seconds. Okay, so Diego's time, 30 seconds. Diego's distance, 50 meters. All right, number 2, or letter B, Lynn left the ticket booth at the same time as Tyler. So again, she should be here at 0, 0. All right. And then she ran at a steady pace and arrived at the bumper cars in 20 seconds. Okay, so that's why they filled out here in her table. 20 seconds, 50 meters. All right. So, and then May, the third one, letter C, we're actually not going to do this one just for sake of time so we can make sure we have plenty of time to do other stuff. So we're not going to do May's. We're just doing Diego and Lynn's time, and we're going to see how that compares to Tyler's. All right. So, to do this, the first thing I want you guys to do is fill in the rest of these tables that are missing. Okay, so that means you're going to have to find the constant of proportionality, find what you're multiplying time by to get to distance for both of them, and then fill in the rest of the table. Once you've filled in the rest of the table, then I want you guys to use a unique symbol. So let's just say Diego's time, you're going to use an X, okay? X marks the spot for him. So whenever you plot points, you're going to use an X instead of a dot. And whenever you're using Lynn's time, you're going to use a little colored in square to represent Lynn's time. So whenever you plot points for Lynn's time, you're going to plot them as a square. Whenever you plot Diego's time, you're going to plot them as an X. Instead of using different colors, we're going to use different symbols. It'll be a little quicker for us, okay? So on your own, fill in the rest of the tables, and then transfer that information to the graph. You can use calculators as well. Ready, set, go. So find that constant of proportionality and then apply it.
I don't know what number. Ryan, what number? I can't tell what number. 21. What number? 18 now.
Great. Yeah.
Wait, can I just get my calculator?
Yeah. What's up?
The same thing that happened to my computer.
Oh, really?
And I can't get it. And it's working it, so it kind of like slid out. So I have to take
There
that. Yeah, it works.
Okay, so find that constant of proportionality. Hey, so everyone should be working on their own, Vickers. Ready? Just check this out. You know how to find the constant of proportionality? Just checking. So what are you going to do to find it here?
Figure out what time this is this.
Yeah, how are you going to figure that out, though?
Division?
Division, yeah, so you do 50 divided by 30, and that'll tell you what point that was.
Good. Yeah, and just put 1.6 for P, just like triple R over.
about 30 times length equals 50. So work back. You think about it like this. Again, use different symbols for Diego and for Lynn. So Tyler, I just used a dot to show his point up here, but use an X for Diego and a square for Lynn so we can all be on the same page here. So for example, Diego, I'm going to use the X, 30 and 50. So 30 seconds, 50 meters. This is Diego. This is Lynn. Just use the side of your book or your plan. Use your plan. How you doing? Need help? Okay. Well, you were talking to Maria over there, so I assumed you needed some help. Oh, well, we don't talk when we're doing individual work. Okay. So. Yeah, that's it. That's it. Yeah, this is 1.6 repeat. Okay. So that's it. So then you can, so it's multiplied by 1.6 to get this way, right? Okay. So you do 15 times 1.6 repeat. And you could just do 15, which is 15.
I got 1.2905.
1.6 in there. Boom. Give me 24.9, round that up to 25.
So now we do 4,000.
No, just put 1.620. Yes, and then once you have plotted all the points and you've drawn their lines, make sure you draw a straight line from each person's finishing time through the origin. Nice, that's good. And then answer number 3. So number 3 is asking who is moving the fastest. Have you this one yet? You're trying to figure out 20 times what equals 50. Work backwards. Do 50 divided by 20. Boom, you got 25. So, or 2.5. 2.5, exactly. So that's going to be this. So whatever you multiply this side by, so that's 2.5 right there. Okay. And then if I multiply by 2.5 here, what do I do to get back? Divide by 2.5, so 25 divided by 2.5. Okay. So, Charlie, what about Diego? How far does he go in 1 second?
He goes 1.6 repeating.
So if you have it as a decimal, it's 1.6 repeating. If you had a fraction, it would be 5/3. But both of those numbers describe the same thing. Okay, perfect. So then, Diego, after 15 seconds, how far has he gone, Maria? 24. It was probably 24.9 repeating, which we're going to round to 25. Okay, so that's 25 meters he's able to go. And then if 0 time has gone by, then Adam Reitz is, I mean, remove her from that. Then Dana, how far has he gone in 0 seconds? 0, right? Yeah, because he's still there and they all leaving at the same time. So 0 seconds have gone by. He's gone 0 seconds, or he's gone 0 meters. So now we have enough to fill in his graph here. His line representing how fast he's going. So we know that after 15 seconds, okay, 15 seconds is down here, he was able to go 25 meters. Okay, so I'm going to put a little X right here to represent his journey. All right, and then I'm going to use a straight edge to show that he starts at 0, 0, and his line goes through his 2 points there, and that's when he is able to finish his race, or he's able to arrive at the bumper cars. Okay, now for Lynn, on the other hand, Tate, how far can she go in 1 second?
She could go 0.4.
0.4 meters, or you can write that as 2/5 of a meter. All right, now if Lynn can go 0.4 meters in 1 second, how long does it take her to go 25 meters, Dakota? It would take her 10 seconds, exactly. And then Lynn, if she has gone 0 meters, well then, Larkin, how much time has gone by? 0. Yeah, that makes sense, right? So each one of these is going to start at 0, 0. Remember that if it's a proportional relationship, all these lines should go through 0, 0. So I can go ahead and draw my line. It's actually going to end right here because they are bumper cars. And then I'm going to fill in 10 and 25. 10, 25 right here. Okay. Now, once I have this, I want you guys to take a look at this. And what I'd love to hear from you, Gabby, is who do you think is moving the fastest?
Who do I think is moving the fastest? I think it might be Lynn.
Think it might be Lynn. I would agree. So the way you can look at speed in 2 different ways. So I want everyone to look up on the board now because this is kind of a visual point I would like to make. So Yasleen, take a look at this. Karina, take a look at this. Dana, you're going to need to see this. Now you can look at speed in 2 different ways. You can either say, well, how much time does it take to run a particular amount of distance? So that would be like if I said, everyone in this class, we're all going out to the track and we're all going to run 1 mile. And then whoever takes the least amount of time is running the fastest. So that's kind of like what these guys are doing, okay? So if I were to draw a line straight across at 50 meters, okay, this is the finish line. Karina, make sure your eyes are up here. Okay, if this is the finish line right here, all right, then I say, well, who gets there the fastest? Well, it looks like Lynn got there in 20 seconds. Okay, so Lynn, it took her this amount of time. All right, Karina, eyes up here. Thank you. Put the pencil down. All right, and then it took our friend Diego this amount of time. Took him 30 seconds, and Tyler was the slowest. It took him 40 seconds, okay? So that's one way you can look at speed. A defined distance, who gets there fastest is going, who gets there soonest in the least amount of time is going the fastest. Here's another way you could look at this. You can look at speed in terms of time. So this would be like if I said, okay, everyone on the track, we're going to run for 10 straight minutes. And then at 10 minutes, I blow a whistle and see who has gone the furthest. That person will have been traveling the fastest. Okay, so that would be like if I were to take this graph and I were to draw a line right up here at 20 seconds. Okay, so I say, okay, Tyler, Lynn, and Diego, you are going to run for 20 seconds straight. And after 20 seconds, Lynn has made it all the way to the bumper cars, 50 meters, okay? And then if we go down, though, Diego, he's right about here. So if I draw a line over, looks like Diego was only able to run about 35 meters, okay? And then Tyler, he's all the way over here. Let's see. And he's just below this mark, so it looks like he's just below 25. So I'd say he was about to go 24. So it looks like Tyler went 24 meters, Diego went 35 meters, and Lynn went 50 meters. So you can look at speed in 2 different ways. A specific amount of time, who can run the furthest. A specific distance, who gets there the fastest. Okay, so you can look at time 2 different ways. But it doesn't matter which way you look at it, Lynn is traveling the fastest in this scenario. All right, let's look at some other graphs. Next one. So this next one's talking about space rocks and the price of rope. This first one is space rocks. Okay, so we have a meteoroid, Perseid 245, and asteroid X. So they travel through the solar system. The graph shows the distance each traveled after a given point in time. So what I want you guys to do with your shoulder partners is to determine which is traveling faster, asteroid X and Perseid 245, and you need to explain how you know that. How do you know? Just like I explained to you on the last one how I knew that Lynn was traveling faster, how do you know that that particular space rock is traveling faster? Okay, ready, set, go.
asteroid X plus asteroid and then label it this.
Are you just clicking random numbers?
So we're on the next page.
15,000.
Yeah, right here. Okay, so which one do you think is going faster?
This faster.
Why do you think it's going faster? So remember I was just talking about, we can either talk about distance or time. So let's check this out. So let's say this is the distance, right? We're going to draw a straight line across, okay? This is the distance, okay? Now time, as you go on, it goes greater and greater amounts of time, right? This takes a long time, this is a shorter amount of time. So, that's how much time it takes.
So I know what
Asteroid
gravity
X.
is.
That's how much time it takes to say 245. So who goes fastest?
Asteroids quickly.
No, really?
Hey, you don't have a. Hey, you guys don't have descriptions now. Let's go. No. I want you to do this. No, we're not talking about gravity right now. We're talking about speed of an asteroid.
I know, I'm talking about how
Meteoroid.
gravity holds.
Because he made it shorter? That doesn't really make sense. I want you to try to find that answer. Use what I was talking about. If you had a defined amount of distance, who would get there fastest? Or if you had a defined amount of time, who would get there, who would go the furthest? Yes.
No, it doesn't.
Yes, it does.
Yeah, that's the pure save. This is what I'm talking about. Asteroid X is going faster.
I know on Selma, but right down here, Esther X is.
Yeah, I'll take that. Yeah, totally. Okay, everyone's eyes up on the board, and I want to start off with, everyone listen up. So, Larkin, what did you guys say? Which one do you think is moving faster?
We thought asteroid X was going faster.
Why do you think asteroid X is moving faster?
Proceed or whatever, it kind of looks like it's going in a little bit of a curve more than asteroid X is going in like a straight.
Well, I think they're both, I agree with your answer, but I think their reasoning's a little bit off because I think they both are straight lines. So, Zia, did you also say that asteroid X is going faster? Why did you think asteroid X was going faster?
Because the other page, when we was going faster, she was going more up.
Oh, okay, good observation. So, Zia noticed that the steeper the line, when we're talking about distance and time, means that that person was going faster. And I would agree that asteroid X has a steeper slope, and what that steeper slope says, that if they go both the same amount of distance, okay, so let's say I draw a line that's parallel to the timeline, and we'll even do it down here and maybe make it a little easier. If this is our time, or our defined distance, okay, and we don't know what this distance is, but it doesn't really matter. We know that in this same distance, both of these objects are going the same distance, and it takes asteroid X this much time, and it takes Perseid 245 this much time. Obviously, it takes the Perseid 245 more time to go the same distance. All right, now again, I could do this the other way, and I could say, well, here is one chunk of time, okay? They both start at the same time, and then at this time right here, we're going to see where asteroid X is at and where Perseid 245 is at. Okay, well, at that time, Perseid 245 was able to go this distance, whereas asteroid X was able to go this distance. So obviously, the same amount of time, asteroid X was able to go much further. Perseid 245 wasn't able to go that far. Okay, so you can look at it two different ways. All right. Next question is talking about the price of rope. Now, the price of rope, we're talking about either cotton or nylon rope. All right, and this bottom axis here talks about the length of rope, okay? This y-axis here talks about the price of rope. And this question asks, if you were to buy $1 of each kind of rope, which one will be longer? So we don't know what the scale is on price, but let's just say that $1 of rope costs somewhere around right here, okay? We'll say that's $1. Okay, $1 of rope costs about that much. So which one is going to be longer? Which one's going to be longer? Again, with the shoulder partners, ready, set, go. And why? Make sure you explain.
Okay, So you got
What do you think, Sam? Freeze. What do you think? Why? So it's not the length of the line. Did you see what I did up there? Across the dollar? This is a dollar, right here. $1. And that means all the way across this line is $1. Okay? So cotton costs this much. Nylon, or no, sorry, they both cost $1. Cotton you get this much. Nylon you get this much. Change your answer.
I think it's
So
not.
Ashford's are not literal.
Which one do you get more? Yeah, $1 you can only buy this much cotton. At $1, it's saying $1 you get this much cotton. See what I'm saying?
Straight
Right,
line.
because $1, boom, boom, that's
That's straight as
how much you get. All right, Anselmo, if I spend $1 on rope, cotton and nylon, which one do I get more of?
cotton.
Why do you say cotton?
Because on the line, it's like longer than nylon.
True, but the length of the line has nothing to do with the length of the piece of rope.
Well, it's just which one will be longer.
Exactly. So if I spend $1, Anselmo, check this out. Check this out. $1, and I can draw a straight line across on this. $1 is going to cost this much. Okay? Because the y-axis is price. Okay, so that's $1.
Okay.
All right. Now cotton, where it intersects the cotton line is right here. Where it intersects the nylon line is right here. So if I want to find length, that's this axis right here, right? Length.
Yeah.
Okay? So for cotton,
It would be nylon.
I'm able to buy this much. For nylon, the same dollar, I'm able to buy this much. Now, if it's further on over to the right on the L side, that means that's a longer piece of rope. So I can buy more nylon rope for the same amount of money. Does that make sense?
Yeah.
Okay. Now we could look at this a different way if we wanted to as well, and it would be the same thing. Okay, let's say instead I wanted to buy, I went to the store and I said, hey, I want to buy 10 feet of rope for a project I'm working on. 10 feet of rope, okay? Well, let's say 10 feet can be found by this number right here. If that's 10 feet. All right, well, 10 feet of rope is going to cost that much. Or, sorry, 10 feet of rope is going to be that much, and it's going to cost a different amount. Okay, for nylon, 10 feet of rope is only going to cost that much, whereas cotton is going to cost that much. Obviously, as you go further up on the price scale, cotton costs more than nylon for the same amount of rope. Okay, so you can look at this two different ways. Price determining length, or length determining price. Okay. So today's lesson was all about just looking at graphs, trying to pull information from them. And I know it can be kind of awkward and kind of weird, but the more experience you have with looking at graphs and pulling information from them, the better. Because out of everything you learn in math, you're going to see graphs in the media and in advertisements more than anything. And so it's a good skill to have as a consumer in a future citizen of anywhere of the world, to be able to look at data, look at graphs, and be able to read the information for yourself and not be fooled by other people. Okay, that's part of math, is